Okay, so let's try to use this to take some roots of products, like maybe 9 times 4. Well, we can use this rule to immediately write this as square root of 9 times square root of 4, and since 9 is 3 squared and 4 is 2 squared, I get this, which is 6. However, had I wanted to, I might also realize that 9 times 4 is 36, which is 6 squared, which is also going to just give me 6. Either way, we get the same answer, whether or not we make this sort of a realization. Okay. What happens if we wanted to do something like this? Well, not so easy, because the square root of 8 is not a simple number, or radical 8 is not a simple number in some sense. But what can I do? Well, radical 4 is, and 8 happens to be 4 times 2. So what I can do is I can use my rule, and then I can say, hey, since radical 4 is 2, I get 2 times root 2. I actually can't really get any further than this, because root 2, even though we can approximate it, and we can use this symbol to indicate the exact value, there's no sort of simple way I could just magically turn this into a whole number. The problem's done. Root 8 happens to be equal to 2 times root 2. For another example, let's say we wanted something like, I don't know, the root of, 5 over 36. Well, the best that I can do here, use the fact that radical 36 is 6, and I get root 5 over 6. I could rewrite that if I want to do it as a constant multiple of root 5, but these are actually both perfectly good answers. Neither one's really much better than the other. So leaving it in either of these two forms, why can't I go further? Well, I'm not going to get a whole number out of root 5. So I'm going to have to stop at some point, and that point happens to be, well, right here.